Welcome to Late Night History. Settle in. There is nothing you need to do for the next little while except breathe, and let your shoulders come down from wherever they have been all day, and let the room go soft and dim around you. You do not have to follow every word. You do not have to remember any of it. This is a story that will keep whether you stay awake for it or not. And if you drift off somewhere in the middle, that is not a failure. That is the whole point. So loosen your grip on the day. Let the pillow take the weight of your head. And come with me, slowly, downward, into the oldest and quietest place on earth. I want to begin 200 kilometres beneath your feet. Not beneath some far-off mountain range, not beneath the sea, but beneath wherever you happen to be lying right now. 200 kilometres straight down. That is roughly the distance you might drive on a long afternoon, except turned on its end and pushed into the ground, past the soil, past the bedrock, past the layers of stone that hold up cities and forests and the beds of rivers, down through the crust and into the mantle below it. And there, in the dark, at that impossible depth, there is a slab of rock so cold that by every rule we understand, it should have sunk long ago. It should have peeled away and dropped into the hotter churning material beneath it, the way a cold stone dropped into a warm pond sinks straight to the bottom. Cold things are heavy things. Cold rock is denser than warm rock, and denser things sink. That is not a mystery. That is just the ordinary behaviour of the world. And yet this cold slab has not sunk. It has hung there, poised, unmoving in any way that matters, for 3 billion years. Let that number sit with you for a moment, because it is almost too large to hold. 3 billion years. Not 3,000, not 3 million, 3 billion. Long before there were animals with backbones. Long before there was anything walking on land at all. Long before the continents, you know, had taken anything like their present shapes. This piece of rock, colder than the mantle all around it, was already down there, already refusing to fall, already keeping its patient balance in the dark. The oceans have been born and destroyed and born again above it, more times than we can easily count. And still it has not sunk. Empires you have heard of, and empires no one remembers, have risen and crumbled on the thin skin of the world above it, and it has not so much as shifted. It simply hangs there. Cold, heavy, and somehow, impossibly, afloat, this slab of rock has a name, and it is a lovely old-fashioned kind of word. It is called a keel, a cratonic keel. And if you have ever seen a wooden sailing ship, you already understand exactly why. The keel of a ship is the long, deep spine of timber that runs beneath the hull, hidden under the waterline, the part you never see from the dock. It is the thing that keeps the ship upright and steady, that stops it from rolling over in the swell, that lets it ride the water instead of being thrown around by it. And the continents, it turns out, have keels too, deep spines of ancient rock that hang beneath them, hidden far below the surface, keeping them steady, keeping them upright, keeping them afloat on a sea that is not made of water at all, but of slow, hot, flowing stone. The word for the ancient heart of a continent, the oldest and most stable part. The part that has not been folded or torn or remade for billions of years is craton. You will hear me use that word often tonight, so let it become familiar, the way a name becomes familiar. A craton. When that ancient heart lies bare at the surface, scraped clean by ice and weather, we call it a shield, like the great Canadian shield that curves around Hudson Bay, worn smooth and grey and immensely old. And when the same ancient heart is buried under younger layers of sand and mud turned to stone, we call it a platform. Shield or platform, it does not matter for tonight. What matters is the keel that hangs beneath it, the deep root, the long cold spine reaching down into the fire. Now here is the thing I want you to hold on to, the thing that makes this more than just a fact about rocks. When scientists first began to understand that these keels existed and began to measure just how cold they were, they ran straight into a wall, because the numbers did not make sense. Beneath the very oldest cratons, the rock at a given depth is not just a little colder than the rock beneath the oceans. It is a great deal colder, 200 degrees colder, 300 degrees colder. In some places closer to 400 degrees colder than the mantle, at the very same depth, somewhere younger. That is not a small difference. That is the difference between a warm afternoon and a blast furnace, held side by side in the same layer of the earth. The keel is a cold island in a hot ocean. And you can measure this coldness even from the surface, without ever going down there, because cold things give off less heat. Everywhere you go on Earth, a faint warmth is always seeping up out of the ground, so slow and so gentle you never feel it. The leftover heat of the planet's deep interior leaking outward through the rock. Over younger parts of the world, that warmth flows up fairly generously, but over the oldest shields, over the ancient hearts of the continents, the warmth trickling up is noticeably weaker, only a little more than half as much. And that faint, meagre trickle of heat is the surface telling you what lies beneath. It is the whisper of a very cold, very deep, very old root, holding its coldness the way a thick stone cellar holds its chill even on a summer day. So here is the wall the scientists hit. If this rock is that cold, and cold rock is dense, and dense rock sinks, then the keel should have foundered long, long ago. It should have dropped away into the hot mantle beneath it and been swallowed up and lost. The coldest, densest, heaviest part of the whole system should have been the first thing to sink, and instead it is the one thing that has never sunk at all. The keel is the part that endures. The keel is the part that outlasts everything. The coldest rock, which by all rights should have fallen fastest, is the rock that has hung on the longest of anything on the face of the planet. Nobody, for a long time, could say why. And I want you to feel how strange that is, because it is genuinely strange, and it is the kind of quiet mystery that has kept careful people puzzling for their whole working lives. Imagine dropping a cold, heavy iron weight into a pot of warm honey. It sinks, of course it sinks. Now imagine coming back 3 billion years later and finding it still hanging there, halfway down, exactly where you left it, never having reached the bottom. You would not simply shrug and walk away. You would want to know what invisible hand was holding it up. What secret property that iron weight had, that no cold, heavy thing has any business having, that let it defy the most ordinary rule in the world. That is precisely the puzzle of the keel. Something is holding it up. Something we could not see. And the answer, when it came, was so elegant that people still describe it with a kind of hush. But before I tell you the answer, let me do the small thing I always like to do before we go deeper. If you are lying there, listening, warm under the blankets, I would love to know where in the world you are tonight. What country, what city, what quiet room you are drifting off in. Leave it in the comments if you feel like it, sometime when you are awake enough to type. I read them, all of them, and there is something companionable about knowing that this same slow story is unspooling in so many different rooms at once, in so many time zones, over so many people all lying above the very same ancient rock. And if you are new here, and you would like more of these long, unhurried journeys into the deep past to help carry you off to sleep, you are always welcome to subscribe. There is no rush. The stories will keep. Now, back down we go, back down into the dark, to the cold slab that will not sink, and the secret that holds it up. Here is the secret. The keel is cold, yes, but the keel is also, in a way that has nothing to do with its temperature, made of the wrong stuff to sink, or rather, exactly the right stuff to float. And to understand that, we have to go back to how the keel was made in the first place, in the earliest childhood of the Earth, when the whole planet was hotter than it has ever been since. Think of ordinary mantle rock, the deep material the Earth is mostly made of, as a kind of stew. It is not a single ingredient, it is a mixture. And within that mixture, some parts are heavier and some parts are lighter. The heaviest ingredients are the ones rich in iron, and iron is a heavy metal, the same heavy stuff that makes a cast iron pan so much heavier than it looks. The lighter ingredients are rich in magnesium instead, a much lighter metal. In fresh, unmelted mantle, these are all stirred together, the heavy iron-rich parts and the lighter magnesium-rich parts, all in one blend, and the result is a rock of a certain ordinary heaviness. Now, in the young and fiery earth, this deep stew got hot enough to begin to melt. And when a mixed rock like this begins to melt, it does not melt all at once. Evenly, the heavy, iron-rich, low melting point ingredients melt first and drain away as liquid, rising upward, leaving the lighter, magnesium-rich, high melting point ingredients behind as a solid residue. It is a little like what happens if you gently warm a block of mixed fats. The parts that melt easiest turn to liquid first and run off, and what stays behind is only the part that holds its shape at that temperature. The runoff carries away a particular character, and the leftover has a different character entirely. It has been changed. It has been, to use the word the geologists use, depleted. The dense, iron-heavy fraction has been drawn out of it and carried away, up toward the surface to make the crust and the ocean floors. And what remains, sitting there in the deep, is a residue that has had its heaviest ingredient stolen from it. That residue is the keel. And because the heavy iron has been drawn out, and only the lighter magnesium-rich material is left, the keel is intrinsically, permanently lighter than the ordinary mantle around it. Not lighter because it is warm, for it is anything but warm. Lighter because of what it is made of. Lighter in its very composition, forever, no matter its temperature. It is a rock that was born already lightened, drained of its heaviness at the dawn of the world. The rock that makes it has a name, harzburgite, and inside that rock, the crucial mineral is olivine, a green, glassy mineral that makes up much of the deep earth. And there is a simple way geologists score how depleted, how iron-poor a piece of olivine is. They call it the magnesium number, and it is exactly what it sounds like. A measure of how much of the mineral is the light magnesium kind versus the heavy iron kind. In ordinary, fertile, undepleted mantle, that number sits around 89 or 90. But in the olivine of a cratonic keel, the number climbs to 92, 93, even 94. That climb from 90 up to 93 or 4 does not sound like much when you say it aloud. But it is the fingerprint of that ancient melting. It is the record, written into the very crystals, of the day the heavy iron was drawn off and the light residue was left behind. Every degree of that number is a measure of how thoroughly the keel was lightened, and the keels are the most lightened rock of all. How much lighter does this make the keel? Only about 1 or 2%. Again, it does not sound like much. 1 or 2%. If someone told you a loaf of bread weighed 1 or 2% less than another, you would hardly notice. But in the deep earth, where everything is balanced on the finest of margins, 1 or 2% is not small at all. 1 or 2%, it turns out, is almost exactly, almost uncannily, the amount of lightness you need to cancel out the heaviness of being 300 or 400 degrees too cold. And there it is. There is the answer to the whole puzzle. Do you feel it? The keel is heavy because it is cold, and the keel is light because it is depleted. And these two things, the coldness pulling it down and the depletion holding it up, are very nearly the same size. They almost perfectly cancel. The cold says sink, and the composition says float. And the two forces argue each other to a standstill, and the keel simply hangs there, in the balance between them, neither rising nor falling, poised in the dark for billions of years. It is one of the most beautiful ideas in all of earth science, and it has a name too, a name I find genuinely soothing to say. It is called the isopycnic hypothesis. Isopycnic, the word looks forbidding written down, but it comes apart gently once you know it. Iso means equal, the same iso you find in words like isolate or isometric. And picnic comes from an old word for density, for heaviness, equal density. Isopycnic, the keel, though it is far colder than its surroundings, has been made to have very nearly the same density as its surroundings, because its lightness of composition offsets its heaviness of temperature. It floats not because it is light and not because it is warm, but because it has been balanced. It is a rock in equilibrium, a rock at peace with the material around it. It weighs, in the end, almost exactly what the mantle around it weighs, and so the mantle neither pushes it up nor pulls it down. It just lets it be. The person who worked this out, who first argued that the stable old continents must be underlain by a deep root of chemically different, specially balanced mantle, was a scientist named Thomas Jordan, and he laid it out across a series of careful papers in the 1970s and 80s. He gave the deep root a name too, one that has a certain grandeur to it. He called it the tectosphere. The tectosphere, the deep architectural foundation of the continents, the load-bearing structure hidden below. In his earliest estimates, Jordan thought this root might reach as deep as 400 kilometres down. Later work, with more refined instruments, narrowed the strongly anomalous part of the root to something more like 200 to 300 kilometres. But the essential vision was right. Beneath the old continents there is a deep, cold, chemically distinct root, far thicker than anything found beneath the oceans, and it is balanced so finely between its cold and its composition that it neither sinks nor floats away, but simply endures. So when I tell you the keel has hung there for 3 billion years without sinking, I am not telling you it defied the laws of the world. I am telling you something better. I am telling you it obeys them so exactly, so completely, that two opposing laws met inside it and reached a truce. The equation of its survival was written into it at the moment of its making, 3 billion years ago, when the young hot earth melted the iron out of it and left the residue balanced on a knife's edge of neutral buoyancy. It is a self-cancelling sum. Cold minus depletion equals nearly zero. And because that sum came out so close to zero, the keel has never had any strong reason to move, in either direction, ever, and so it has stayed exactly where it began. I find that quietly astonishing, and I hope, lying there in the dark, you do too. Because think about what it means. It means that the reason there is dry land for you to stand on at all. The reason the continents are not simply thin scraps of rock that founder and vanish. The reason there is a stable stage on which every hill and forest and city has ever stood comes down to a piece of arithmetic performed in the deep earth before life had properly begun. A balance struck once, in the beginning, and never disturbed since. The continents ride high and dry and enduring above the deep, not because they are simply old, and not because they are simply thick, but because far below them hangs a root that was long ago balanced against its own weight, and has kept that balance patiently, silently, in the dark, through everything that has happened on the surface since. And what is beneath the keel, holding it up, is the thing the title of tonight's story calls the fire. It is not literally fire, of course. There are no flames down there, no burning in the way you would picture it. But it is the closest thing the deep earth has. Below the cold, rigid, balanced keel lies the asthenosphere, a layer of the mantle that is hot enough and soft enough to flow. Though it flows unimaginably slowly, so slowly that it would take an age to move the distance you could walk in a minute. It is solid rock, and yet over the long reaches of geological time it creeps and churns and circulates, hot material rising and cooler material sinking, turning over and over in the vast slow convection that has driven the drifting of the continents for as long as there have been continents to drift. That is the fire. Hot, mobile, restless rock, forever in slow motion. And the keels ride above it. The cold, still, balanced roots hang down into that churning warmth, their bases brushing against the moving mantle, and yet they are not carried away by it, and they are not swallowed by it, and they are not melted into it. They ride above the fire, steady as ships at anchor, holding the continents up into the light. Two worlds, then, pressed against each other in the deep. Above, the keel, cold, ancient, rigid, still, balanced, unchanging. Below, the asthenosphere, hot, restless, flowing, endlessly turning over. And the boundary between them, the place where the cold, still root meets the hot, moving mantle, is one of the most important surfaces in the entire planet, though no eye will ever see it. It is the waterline of the continent. It is where the keel meets its sea. Everything about whether a continent survives or perishes, whether it rides serenely for billions of years, or is dragged down and destroyed, is decided at that quiet, invisible boundary in the dark. And this is the great enigma we are going to sink into together, slowly, over the hours ahead. Turning it gently in the low light, the way you might turn a smooth stone over and over in your hand until you fall asleep. How does the balance hold? How does a cold, heavy root not only avoid sinking, but resist being scraped away, worn down, carried off by the ceaseless churning of the fire beneath it? A truce between cold and depletion explains why the keel does not sink under its own weight, but it does not, by itself, explain why the restless mantle below does not simply grind the keel away from underneath, the way a river slowly eats the bank it flows against. There must be something more. The keel must be not only balanced, but strong, not only buoyant, but tough. And so there is a second secret waiting for us further down, a second property of this strange old rock, one that has nothing to do with buoyancy at all. But that is for a little later. For now, I only want you to hold the picture, the simple, strange, beautiful picture, and let it settle you as it has settled me so many nights. Somewhere far beneath the room you are lying in, deeper than any mine has ever gone, deeper than any drill has ever reached, there hangs a slab of the oldest rock on earth. It is colder than everything around it. It should, by the plainest rule we know, have sunk into the fire long ago, and instead it hangs there in perfect, patient balance, held up by a lightness that was granted to it at the dawn of the world, riding above the slow churning of the deep, carrying the whole weight of a continent on its cold and ancient shoulders, and asking nothing of anyone. It has done this for 3 billion years. It was doing it before there was anyone to notice, and it will go on doing it long after this night is forgotten. The oldest rock does not strain. It does not labour. It simply is what the beginning made it, balanced against itself, at rest in the dark. There is something in that I find deeply reassuring, lying awake at the end of a long day. That underneath everything restless and burning and always in motion, underneath the churning of the deep and the churning of our own days, there is a foundation that was set right once, long ago, and has held ever since, without effort, without complaint, simply keeping the balance it was given. The continents float on the peace of the very oldest thing. And so, in a way, do you. We have only just begun to go down. There is so much more waiting below us. The second secret of the keel's endurance, the reason it is not only buoyant but unbreakably strong. The strange green fragments of it that ride to the surface inside volcanoes, letting us hold pieces of the deep root in our own hands. The way we can see these keels from the outside, mapping their cold shapes with the trembling of distant earthquakes. And the diamonds that formed inside these keels ages before the volcanoes that carried them up even existed. Diamonds that are older than the fire that brought them, patient passengers riding up out of the balanced dark. All of that lies ahead of us, deeper down, and we will get to it slowly, in no hurry at all. But not yet. For now, just breathe. Let the picture hold you the way the keel holds the continent, steadily, without strain. The cold slab that will not sink, the truce between the cold and the lightness. The balance struck 3 billion years ago and never broken since. Let it be the quiet floor beneath your thoughts as they begin to slow and drift and come untethered from the day. There is nothing down there but stillness and patience and an old balance, keeping faith in the dark. And there is nothing you need to do but rest above it, the way the whole world rests above it, and has always rested above it, and always will. Down we go, a little further. Slowly, there is no bottom we need to reach tonight. Only the long, calm descent and the cold rock that has been waiting, unmoving, since before the beginning of almost everything, to be understood. So let us begin with the strangeness of it, the thing that should not be possible. Cold rock is heavy rock. That is one of the plainest rules the earth obeys. When something in the mantle cools, it contracts, it grows denser, and denser things sink. It is the same reason cold water sinks to the bottom of a pond on a winter night, the same reason a cooling current in the deep mantle will slide downward and pull the warmer material up behind it. The whole slow machinery of the planet's interior runs on this simple habit. Cold sinks, warm rises. And yet here, beneath the oldest hearts of the continents, we find a slab of rock, 200. Sometimes 300 kilometres deep, that is colder than everything around it by 200, 300, even 400 degrees, and it has not sunk. Not in 1,000,000 years, not in 1 billion, not in 3 billion years of the earth turning beneath the stars. It should have foundered long ago. It should have peeled away and dropped into the hot dark, like a stone let go under water. Instead it hangs there, cold and vast and motionless, holding the whole continent up on its back. Think about that for a moment, gently. the way you might turn a smooth stone over in your hand without any need to solve it. The coldest, densest part of the upper mantle, the very piece that by every ordinary rule ought to sink first and fastest, is precisely the piece that has refused to sink at all. For a long time, this was simply a puzzle without an answer, a place where the rules the earth follows everywhere else seemed quietly to stop applying. And I would love to know, before we go any further down, where in the world you are listening from tonight, what dark window this old story is reaching you through. Leave a word in the comments if you feel like it, and if these slow descents help you find your way to sleep, you can subscribe, and there will always be another one waiting. Now, the answer to the puzzle, when it came, was not that the keel is warm after all, because it truly is cold as the numbers say. The answer was that coldness is not the only thing that decides whether a rock sinks or floats. There is a second property hidden inside these keels, and it works in the opposite direction, and the two of them, the cold and the hidden thing, very nearly cancel each other out. That hidden thing is what the rock is made of. Long ago, when the earth was young and its interior ran far hotter than it does today, the material that would become these keels was melted, and melting does something particular to rock. It draws off the heavy part, the iron, the elements that make mantle rock dense and dark and fertile. They melt out first and rise away as basalt, leaving behind a residue that has been stripped of much of its weight. What remains is a rock called harzburgite, a depleted peridotite, and its crystals are unusually rich in magnesium and unusually poor in iron. The mineral people who study these things measure it with a number, the magnesium number. And where ordinary mantle sits around 89 or 90, this old depleted keel rock climbs to 92, 93, 94. It sounds like a small difference. It is a small difference. Somewhere around 1 or 2% lighter than the rock it floats in. But 1 or 2% is exactly enough. Because here is the balance, and it is one of the most elegant things the deep earth has ever arranged. The cold of the keel makes it want to sink. The chemical lightness of the keel, that iron poverty, that missing weight, makes it want to rise. And these two urges are so closely matched that they very nearly erase one another, and the keel is left hanging in the mantle at almost exactly the density of everything around it. Neither sinking nor rising, poised, neutral, still. The man who first understood this was a geophysicist named Thomas Jordan, who gave the deep root its name, the tectosphere, and who proposed that the balance was no accident but the very thing that lets old continents endure. He called it isopycnic, a word that means, simply, equal density. Equal density. The keel weighs, in the end, just what the fire around it weighs, and so the fire cannot swallow it, and the surface cannot lose it, and it stays. Sit with the shape of that for a while, because it is the whole quiet heart of everything that follows. An equation written into the rock 3 billion years ago in a single act of melting that has been solving itself silently every second since. Cold pulling down, lightness holding up. The difference between them almost nothing at all. And on the strength of that almost nothing, on that razor-thin truce between two enormous forces, whole continents ride above the churning, molten, endlessly moving mantle beneath, the layer we call the astenosphere, the slow, hot river of rock that carries the plates and destroys the ocean floors and remakes the face of the world. Above all that fire, the continents float, unbothered, ancient, kept aloft by a balance so fine you could almost call it a kind of grace. But buoyancy alone does not explain the whole story. And here, if you are still awake, is where the account deepens in a way that most treatments of this subject simply pass over, because they stop at the floating and they do not ask the harder question. Floating is necessary, but it is not sufficient. The mantle beneath the keel is not still. It convects slowly over millions of years, but inexorably in vast looping currents that rise where they are hot and sink where they are cool, that pull and drag at everything in contact with them. A piece of wood placed on a moving river does not merely need to be less dense than water. It needs to resist being dragged under at the bends, needs to resist the current that would pull it sideways and tuck its leading edge down into the depths. Buoyancy is the first requirement, strength is the second. And the cratonic keel, it turns out, possesses both, and for reasons that are tangled together in a way that should by now feel almost familiar. Because the same property that gave the keel its chemical lightness also gave it its extraordinary mechanical toughness. When the early Archean mantle melted and surrendered its basaltic fraction, leaving behind that iron-poor magnesium-rich residue, that harzburgite, it did not only remove weight, it removed water. The melting process that extracted the dense iron-bearing minerals also drove off most of the hydrogen that had been locked inside the crystal structures of the olivine, the most abundant mineral in the keel. Water in olivine is not water in the sense of a liquid sitting in a pocket. It is hydrogen atoms bonded into the mineral lattice itself, just a few hundred parts per million by weight, sometimes less, but enough to matter enormously. Because water, even in those trace concentrations, acts as a kind of internal lubricant. It allows the crystal planes of olivine to slide past one another. It reduces the temperature at which the mineral begins to flow. It makes olivine soft in the way that a single drop of oil on a stiff hinge makes the hinge swing freely. And the Archean melting event that depleted the keel of iron also, in the same act, dehydrated it, dried it out, removed almost all of that internal lubricant, leaving an olivine so water-poor, so dry and rigid, that it behaves like something very close to a permanent solid, even when the temperatures around it climb high enough to make ordinary mantle rock flow like cold honey. The scientists who measured this, who went and actually quantified the water content of olivine grains sampled from deep inside cratonic keels, brought to the surface inside kimberlite eruptions, found concentrations of hydrogen that were dramatically lower than in olivine from younger or oceanic lithosphere. The work of researchers like Suzanne Peslier and others who have examined these specimens established that the dry condition of cratonic olivine is not a minor difference, but a fundamental one. The kind of difference that changes the viscosity of rock by orders of magnitude, that changes whether something flows or stands, whether the mantle can grip it or finds nothing to hold. And the mineral physicist Shun Ichiro Karato, among others, helped make precise the relationship between water content and olivine's mechanical behavior. The physics of how crystals deform, how their internal defects migrate under stress, how the presence or absence of dissolved hydrogen changes all of that, this is the field called olivine rheology. And what it says about dry, depleted olivine is simple enough to hold in mind even at this hour. Dry olivine, at the temperatures and pressures inside the keel, has a viscosity orders of magnitude higher than wet olivine at the same conditions. It flows, in effect, not at all. It is, for practical purposes, on the timescales that geological processes operate, a rigid body. and a rigid body embedded in a slowly convecting fluid resists being entrained by that fluid with far greater stubbornness than a softer one would. So here is what the keel is. It is cold, which makes it dense enough to threaten sinking, and that same coldness keeps the olivine well below any creeping temperature. It is depleted of iron, which makes it light enough to counteract the cold density, and that same depletion dried out the olivine, leaving it stiff beyond what any wet rock achieves. The buoyancy and the strength are not separate gifts. They came from the same moment of melting, in the same act. The Archean furnace that made the keels light also made them hard, and these two properties have been reinforcing one another for billions of years. The chemical lightness keeping the keel from sinking into the convecting mantle below, the mechanical strength keeping the convecting mantle from eroding the keel away from the sides and the base, one property guarding the other, round and round, a self-reinforcing armour written into the rock in the first few billion years of Earth's history and never since undone. Or almost never. But that story waits a little longer. What remains is the question of how we know any of this. How do we know what rock is made of at 200 kilometres depth, at pressures that would reduce a car to a flat object the size of a credit card, at temperatures hot enough that the rock would flow over any human timescale, but cold enough that a diamond remains diamond and not graphite? How do we know? And the answer is that the Earth itself occasionally provides samples. Not by any human intervention, not by drilling. No drill has ever reached more than about 12 kilometres, barely scratching the skin, but by a geological process so strange and violent and poorly understood in its precise mechanics that it deserves a moment of unhurried attention. There are volcanoes, and then there is something different from a volcano, something that behaves so peculiarly, so explosively, so fast, that scientists give it its own name. A kimberlite. Kimberlites are rare eruptions that originate not from the shallow melting that feeds ordinary volcanoes, but from far deeper, somewhere in the vicinity of 150 kilometres or more, rising from within or just below the base of the cratonic keel itself. They are not especially dramatic at the surface. They do not build the towering cones of basaltic volcanoes or the apocalyptic calderas of supervolcanoes. They form what geologists call diatremes, carrot-shaped pipes driven upward through the crust by a mixture of magma and gas, mostly carbon dioxide, moving at extraordinary speed. The estimates for how fast a kimberlite rises vary, but they converge on something remarkable: meters per second, not centimeters per year, as magmas typically move when they filter slowly upward through rock. Meters per second. A kimberlite can rise from 150 kilometres deep to the surface in a matter of hours, perhaps a single day. The geological equivalent of a bullet passing through a body before the body has time to respond. And this speed is not incidental, it is essential, because as the kimberlite rises, tearing upward through the lower crust and then the upper crust, and finally bursting into the open air, it rips chunks of rock from the walls of the pipe and from deeper levels below the crust. These chunks, these torn fragments of the keel itself, travel upward inside the kimberlite magma like passengers in a very violent, very fast elevator. They are called xenoliths, from the Greek for foreign rock, because they are foreign to the magma that carries them, foreign to the volcanic pipe in which they are eventually found, visitors from depths no human process has ever reached directly. And if the kimberlite ascends fast enough, which it must and does, those fragments arrive at the surface mostly intact, crystalline structures preserved, mineral chemistry locked in, a sample of the deep earth delivered to the feet of geologists who have, over the last century or so, learned to read them with extraordinary precision. The dominant rock type in these samples from cratonic keels is peridotite, specifically a variety called harzburgite, that depleted residue we have already met. Olivine-rich, poor in the calcium and aluminium and iron that were removed when the basaltic melt was extracted. Sometimes the xenoliths are eclogite, a dense rock that represents ancient oceanic crust that was subducted long ago and lodged in the deep keel. A completely different history preserved in the same carat of stone. And within these xenoliths, within the individual crystals, geologists find the information they need. The technique is called geothermobarometry. It is, at its core, a thermometer and a pressure gauge built from mineral chemistry. When two minerals crystallize in contact with one another at high temperature and pressure, they exchange elements between their crystal structures in proportions that depend precisely on the temperature and pressure at which the exchange happened. When the minerals are quenched, rapidly cooled by a fast-rising kimberlite, before they have time to re-equilibrate, those proportions are frozen in, like an insect in amber, preserving a record of the conditions in the deep keel at the time the rock was formed or last equilibrated. By measuring the proportions of certain elements between adjacent minerals, iron and magnesium between olivine and garnet, for instance, or calcium between pyroxenes, geochemists can calculate to within a few tens of degrees and a few tenths of a gigapascal, the temperature and pressure at which that particular sample last equilibrated. When geologists do this for many xenoliths from the same kimberlite, plotting each sample's reconstructed temperature and pressure on a graph, they recover something called a geotherm, a curve that traces how temperature changes with depth inside that particular piece of lithosphere. And the geotherms recovered from xenoliths of old cratons look unlike anything found beneath oceans or young continents. They are cold, strikingly, anomalously, unmistakably cold. At any given depth, the temperature inside the cratonic keel is hundreds of degrees lower than it would be at the same depth beneath a young mountain belt or beneath the ocean floor. The line on the graph falls far to the left of where normal mantle sits, tracking a cold, conductive gradient that descends steadily into the deep earth, and then bends at the base of the lithosphere. To rejoin the steeper adiabat, the temperature profile of the convecting mantle below and the point where it bends is the lithosphere-astenosphere boundary. The base of the keel, readable in the chemistry of a fragment of rock brought up in a magma pipe. As legible as a letter written in a language geologists have spent decades learning to read. The surface heat flow over these old shields, the rate at which warmth leaks upward through the crust and escapes into the air, tells the same story from the opposite direction. Over the Archean cores of continents, the Canadian Shield, the Kaapvaal, the Pilbara, the old heart of Siberia, surface heat flow runs at around 40 to 50 milliwatts per square metre. That is a small number. Over younger continental regions, over active rifts and recent mountain belts, and young volcanic provinces, heat flow can reach twice that or more. The old cratons run cold all the way from the deep keel up to the ground. They are, in a thermal sense, quiet, insulated from the fire below by the very thickness of the cold root that hangs beneath them, losing so little heat to the surface that the rocks above have remained, geologically speaking, almost undisturbed for billions of years. And there is a third way of seeing the keels, one that requires no samples, no drill bits, no exposure of rock at all. It sees through the entire Earth the way an X-ray sees through a hand, by measuring not physical specimens but the behavior of sound, seismic waves. When an earthquake strikes anywhere on Earth, it sends vibrations propagating outward in all directions, shear waves and compressional waves, moving through the planet's interior at speeds that depend on the density and stiffness of whatever material they are passing through. Cold, depleted mantle, like the cratonic keel, is stiffer and slightly denser at any given pressure than hot, fertile mantle, and so seismic waves, particularly the shear waves, travel faster through it. A seismometer on the far side of the Earth records the arrival of those waves, and from thousands of such recordings, at thousands of stations, over decades of earthquakes, geophysicists can reconstruct, through a process called seismic tomography, a three-dimensional map of the wave speeds inside the Earth, and hence a three-dimensional map of where the mantle is anomalously cold and stiff, and where it is anomalously hot and soft. The cratonic keels appear on those maps as lobes of fast-moving seismic waves, descending from beneath the old Archean shields to depths of 200, sometimes 250 kilometres, occasionally approaching 300. They are not subtle features. They are among the clearest, most consistently reproduced signals in global seismic tomography, present in every model, refined as the networks of seismometers have grown denser and the mathematical inversion techniques have grown more sophisticated. The models have names. SL2013 ZSV is one of the better-known global shear velocity models, and they show the same thing over and over again. Beneath the Canadian Shield, beneath southern Africa, beneath the old hearts of Australia and Siberia and the Baltic, there are these cold, fast, deep roots hanging in the mantle, and beneath the oceans and the young continents there are none. And the keels are not confirmed by tomography alone. There is another way of looking, one that responds not to the passage of sound, but to the passage of electrical current, or rather to the way the Earth resists such passage. The technique is called magnetotellurics, and it uses natural variations in Earth's magnetic and electric fields, generated by interactions in the upper atmosphere and by the planet's own interior, to probe the electrical conductivity of the crust and upper mantle below. Dry, cold, depleted rock is an excellent insulator. Hot, wet, partially molten rock conducts electricity far better. Magnetotelluric surveys across cratonic shields consistently find an anomalously resistive zone extending to great depth, the same depth range, the same lateral extent as the fast seismic anomalies, a cold, dry, rigid body that blocks electrical current the way a thick rubber mat blocks it. A measurement of heat flow here, a xenolith geotherm there, a seismic tomography image above. A magnetotelluric resistivity profile alongside 4 independent techniques, 4 different physical properties, all pointing at the same object in the same place at the same depth, all saying the same thing. There is something down there. It is cold. It is stiff. It is not moving. It has been there a very long time. That last point, how long, is the most important point of all, and the one the field had to work hardest to establish. Because the isopycnic hypothesis and the seismic images and the xenolith geotherms all describe what the keel is like today. They tell you it is cold and depleted and buoyant and strong. They do not by themselves tell you when it formed, or whether it formed at the same time as the ancient crust above it. One could imagine a scenario in which the crust of the Canadian Shield formed 3 billion years ago, and then, much later, in some slow geological accumulation, acquired a deep root of depleted mantle beneath it. A root added later, a separate piece stuck on from below, not born with the crust, but accreted to it over time. If that were true, the keel would be a secondary feature, something the continent acquired after the fact, not its original ballast. The answer to this question came from the same laboratory that eventually provided so many answers about deep earth chemistry. It came from the analysis of tiny mineral grains inside the xenoliths. From isotope ratios measured with mass spectrometers of extraordinary precision, from a radiometric clock based on two elements, rhenium and osmium, that behave in a way peculiarly suited to tracking the history of depleted mantle. Rhenium and osmium are both rare metals present in mantle rocks in trace concentrations, and rhenium decays radioactively to osmium over long timescales in a way that geochemists can use as a clock. In fertile, undepleted mantle, rhenium and osmium accumulate in characteristic ratios that evolve predictably over time. But when mantle rock is melted and the basaltic fraction is extracted, when it is depleted in the way the cratonic keel was depleted, rhenium, which is more mobile than osmium, is preferentially removed with the melt. The depleted residue is left with a very low rhenium to osmium ratio, essentially freezing its osmium isotopic composition at the value it had at the time of depletion. It stops evolving in isotopic terms at the moment of the melting event. The osmium isotopic composition of a piece of depleted mantle is therefore a clock that stopped ticking at the moment the depletion happened, the Rayos model age, and reading that clock tells you when the keel material was made. Geochemists have measured Rayos model ages from sulfide minerals and olivine grains separated from cratonic mantle xenoliths. Those fragments of keel brought up inside kimberlites, and what they find is remarkable and, once you understand it, very moving in the way that only deep time can be moving. The Rayos model ages from xenoliths beneath the Kaapvaal Craton cluster around 3 billion years, some reaching higher. The Rayos model ages from xenoliths beneath the Slave Craton in Canada similarly reach back into the deep Archean. And when you compare those ages to the ages of the overlying crust, the crust of the Kaapvaal, which is between roughly 3.6 and 2.7 billion years old, dated by uranium lead methods on zircon crystals in the surface rocks, they match. The keel material and the crustal rock above it record the same ancient events, the same window of time in the Archean, separated by 200 kilometres of depth, but united by the same birth. They are the same age. They formed together. The keel is not an afterthought added below an old crust. It is the original ballast, born in the same Archean event as the continent it carries. The deep root and the surface rock, two parts of one raft, assembled as a single entity 3 billion years ago and surviving together ever since. This is the finding that makes everything else cohere. Because if the keel formed later, separately, then you might argue the continent could survive without it, that the crust above is what matters and the root below is incidental. But if the keel and the crust formed together as one coupled system, then removing the keel is removing something foundational, something without which the continent is no longer what it was. And the evidence from Rio's geochronology says they did form together, that the Archean melting event that created the depleted, buoyant, dry mantle root was the same event, or very closely related to the same period of events that built the thick, silica-rich, ancient crust riding above it. A continent is not a surface thing with an incidental underside. It is a pair, crust above, keel below, age-matched and inseparable, the way a ship's hull and its keel are not two separate objects, but one structure whose integrity depends on both. And within that structure, within the cold interior of the keel, sitting at depths and pressures and temperatures that exist nowhere else in the volume of rock accessible to human investigation, there are objects that have been waiting in the dark longer than most things on the surface of this planet have existed. They are not large, they are not spectacular at the depths from which they come. But they are perhaps the most remarkable objects a person can hold in a hand, because they are seals, airtight, pressure-proof, chemically inert containers that have held their contents unchanged through more billions of years than most minds can comfortably contain. They are the subject that the next movement of this account will enter. Slowly, carefully, as the night deepens and the body settles further into rest. But before we descend to them, sit for a moment with what has been established. Let it settle the way the keel itself has settled into the mantle, quietly, over an incomprehensible span of time. The keel is buoyant because it is chemically depleted. It is strong because that same depletion dried it out. Its dryness is confirmed by measurements of water content in xenolith minerals. Its coldness is confirmed by the geotherms reconstructed from those same xenoliths, by the low heat flow leaking upward through the shields above, by the fast shear wave anomalies that seismic tomography maps to depths of 200 and 300 kilometres, by the high electrical resistivity that magnetotelluric surveys find in exactly the same places. And its age is confirmed by rhenium-osmium isotope ratios in mantle sulfides that match the ages of the ancient crust riding above, proving that the keel and the continent it carries were born as one thing, in the Archean, and have travelled through every geological upheaval since as one thing. Together, indivisible, the asthenosphere moves beneath the keel in its slow, hot, roiling currents. The plates shift above. Oceans open and close, mountain ranges rise and are worn to plains. Ice ages come and strip the land and retreat and leave their scratches in the rock. And through all of that, the keel hangs in the mantle at almost exactly the density of the mantle around it, neither sinking nor rising, cold and dry and rigid and 3 billion years old, riding above the fire, keeping the continent aloft, asking nothing of us and needing nothing from the surface world. Simply persisting in the dark, at pressures and temperatures we have no language comfortable enough to hold. It is very quiet down there. Or it would be if quiet were a concept that applied to rock at 200 kilometres depth, where there is no air to carry sound, no space for vibration in the ordinary sense. The rock simply is, as it has always been, a self-cancelling equation balanced on the edge of a razor, the coldness pulling down and the lightness holding up, and the two forces meeting each other so nearly exactly that the difference across 3 billion years has amounted to almost nothing, and the continent above has not sunk, and the shields have not folded, and the oldest rocks still sit where they were deposited in seas that have since dried and been replaced and dried again, and the keels beneath them have not moved, not in any way that matters, not in any direction the story needs to account for. Somewhere in the lower levels of this cold, rigid, ancient column of depleted rock, at depths below 150 kilometres, In conditions of pressure that would require a force of more than 45,000 atmospheres applied to a single square centimetre of surface just to replicate, there are crystals that formed from carbon atoms arranged in a particular way. Their bonds aligned in 3 dimensions with a geometric precision that makes them the hardest natural material on Earth. They formed there, in the dark, under pressure, over geological timescales, and they have been sitting in the cold interior of the keel ever since, sealed away from the heat that would have converted them to graphite if they had sat anywhere hotter, preserved by the same cold geotherm that the xenolith minerals record, waiting in the deep root of the continent the way a message waits in a sealed envelope, carrying inside them inclusions of even older minerals, fragments of the mantle and sometimes of subducted ancient seafloor, chemistry that has not changed since it was locked inside those crystals, sometimes 3 billion years ago or more. And then, one day, one geological day, which might mean any moment in the last several 100 million years, a pulse of magma forms at depth, carbon dioxide rich and mobile, and begins to rise. It rises at meters per second. It tears through the base of the crust and up through the column of rock above, widening as it goes. The decompression and the gas generating a violence disproportionate to the scale of the eruption at the surface, and as it moves it picks up fragments of the keel, chunks of peridotite and eclogite and everything else in the walls of the pipe it is tearing upward, and among those fragments, caught up and carried along, are the crystals that have been waiting in the dark at 150 kilometres for 1 billion years. And within those crystals, locked inside their rigid lattices, are the inclusions, the sealed record of the deep earth at the time those crystals formed, that geochemists will one day cut and polish and dissolve and measure and argue about in journals and at conferences and late at night in laboratories. But that story, the story of what those inclusions contain and what they tell us about the age of the keel and the early history of the planet and the deep cycling of water and carbon, that story opens in the movement that follows this one. For now it is enough to know that the containers exist, that they are old beyond easy imagining, and that the cold, rigid, buoyant keel that has been the subject of this long descent is the only place on Earth cold enough and stable enough and ancient enough to have held them safe. The night is deep enough now. Let the picture rest for a while in whatever level of the mind is still receiving it. There are 2 places on Earth where the argument for the keel's reality is no longer abstract. No longer a matter of seismic velocities and density equations and theoretical geotherms, but a matter of geography and stone and the particular darkness of a mine shaft running down through the oldest rock a human hand has ever touched. One of them sits in the far north of Canada, where the land is flat and cold and vast, and scattered with lakes that reflect a sky in which the aurora sometimes moves. The other sits in the south of Africa, where the grassland is dry, and the light is hard, and the ground beneath the grass conceals a history older than almost anything you could name. Both of them are places where the keel is not an abstraction. Both of them are places where you can hold the evidence in your hand. Begin, if you like, in the south. The Kaapvaal Craton occupies a large portion of southern Africa, roughly the region that today corresponds to eastern South Africa, Zimbabwe, Swaziland, and portions of neighbouring countries. And it is among the best studied pieces of ancient continental crust on the planet, in part because of its geology, and in part because of what that geology contains. Its crust is Archean. The rocks that form the uppermost layer of this craton, the rocks that farmers have ploughed around, and miners have drilled through, and geologists have dated with the patient tools of isotopic chemistry, were formed between roughly 3.6 and 2.7 billion years ago. To put that in terms that have some purchase on the imagination, when the oldest of those rocks were crystallizing from cooling magma at the surface of the early Earth, the moon was visibly larger in the sky than it is now, because it had not yet drifted to its current distance. And the oceans that covered most of the planet's surface were chemically unlike any ocean that exists today, and there was almost no free oxygen in the atmosphere, and the entire history of recognizable life, everything from the first worm to the last human thought, lay in a future so remote it could not meaningfully be said to be coming. And the keel beneath the Kaapvaal is roughly as old as the crust above it. That correspondence is not accidental, and it is not obvious, and it took decades of careful measurement to establish. What the measurements show, and they are measurements of rheos isotopes extracted from sulfide minerals and olivine grains in mantle xenoliths collected from kimberlite pipes across the Craton, is that the mantle beneath southern Africa, the thick, cold, depleted root whose existence you have by now had time to absorb through the long descent of this narration, formed at roughly the same time as the crust it carries. The ages converge. The mantle peridotites from the Kaapvaal keel return os model ages of approximately 3 billion years, matching within reasonable uncertainty the overlying Archean crust. What this means, stated plainly, is that the keel is not something that attached itself to the Craton afterward, not a later acquisition, not a deep root that grew beneath an existing continent over some separate chapter of geological history. The keel and the crust are the same age because they were born together. They are a single raft. And it is a raft that has endured through 3 billion years of Earth history, through the opening and closing of oceans that no longer exist, through the assembly and fragmentation of supercontinents whose names most people have never encountered, through the slow drift of the African landmass across the face of the planet, and the collision of tectonic plates and the rise of mountain belts that have long since eroded to plains. The Kaapvaal Craton has remained. It has remained coherent, which means it has not been torn apart. It has remained at the surface, which means it has not been dragged down. It has remained cold, which means the olivine in its keel has stayed rigid and dry and resistant to the convecting mantle beneath it, and which also means that the conditions inside its deep interior have remained, across all of that time, within the narrow range in which carbon can persist in its dense, high-pressure form rather than converting to something looser and lighter. Which brings us to the mines. The Kimberley district of the Northern Cape province of South Africa is, by almost any measure, the place where industrial diamond mining was born, and the word kimberlite, the volcanic rock that delivers diamonds to the surface, is named for this town, which is itself a relatively recent thing. A Victorian-era settlement, grown up around the discovery in 1871 of what turned out to be one of the most diamond-rich localities ever found. The Big Hole at Kimberley, dug by hand and later by machine, is by some reckonings the largest hand-excavated hole in the world, and it represents the work of many thousands of people over many decades extracting rock from the upper portion of what had once been a kimberlite pipe, the carrot-shaped conduit through which magma had risen from the mantle and erupted at the surface at some point in the geologically recent past. Geologically recent meaning, in this context, roughly 90 to 100 million years ago. And yet the diamonds in that pipe, The diamonds that came up through it, that rode inside the magma as it tore through 150 kilometres of rock in a matter of hours, those diamonds are not 90 to 100 million years old. They are nothing close to that age. But let that thought wait for a moment, because it wants the right frame around it when it arrives. Several hundred kilometres to the northeast of Kimberley, in what is now Gauteng province, lies the mine historically known as the Premier Mine, and more recently as the Cullinan Mine, named for the town that grew around it. The Cullinan Mine is the source of the Cullinan diamond found in 1905, the largest gem-quality rough diamond ever recovered, roughly 3,106 carats in its uncut form, and it is the source of stones that now sit in the British Crown Jewels. But the mine's significance to the science of the keel has nothing to do with the size or the beauty of the stones it has produced. Its significance is that its kimberlite pipe, like the Kimberley pipes, erupted through the Kaapvaal Craton, through rock whose Rios ages reach back 3 billion years, and that the diamonds it has yielded have been subjected to the same isotopic analysis that has been applied to diamonds from kimberlites around the world, and that the results of those analyses have contributed to the slow, careful, laboratory-built argument that diamonds are not made by the volcano that delivers them. They are carried by it. Now let that frame arrive. When a kimberlite magma rises, it does not rise through empty space. It rises through the keel. It tears loose fragments from the walls of the conduit it is opening. Those are the xenoliths, the hitchhiking chunks of peridotite and eclogite that geochemists extract from kimberlite rock and analyze for the temperature and pressure at which they last equilibrated with their surroundings. And among the material it carries, embedded in the xenolith fragments or simply caught up as loose crystals in the magma itself, are diamonds. Diamonds that were sitting in the keel, stable and inert and sealed, at depths greater than 150 kilometres, for a very long time before the magma arrived. How long? The answer comes from the inclusions, those microscopic minerals trapped inside the diamond crystals at the moment the diamonds grew. Because diamonds are among the most chemically inert substances in nature, and because the crystal lattice of diamond is rigid and dense, and does not permit the entry or exit of atoms once it has formed, whatever was present when the crystal grew is still present, sealed inside, unchanged by the billions of years of heat and pressure and geological event that have taken place since. The inclusions are samples of the deep earth as it was when the diamond formed. And because some of those mineral inclusions contain elements whose isotopes decay at known rates over geological time, in particular rhenium decaying to osmium in sulfide inclusions, and samarium decaying to neodymium in silicate inclusions, it is possible to extract them, measure their isotopic ratios, and calculate when the diamond grew. The ages that emerge from those measurements are extraordinary. Peridotitic diamonds, the type that grow in the depleted iron-poor material of the keel itself, typically return ages ranging from roughly 1 billion to more than 3 billion years, with many clustering in the Archean and Proterozoic, the earliest chapters of Earth history. Some diamonds from the Kaapvaal keel carry os ages that approach 3 billion years. Some from other cratons push toward 3.5 billion. And many of the kimberlite pipes that delivered these diamonds to the surface have eruption ages of only a few 100 million years, or a few tens of millions, or in some cases less than that. The gap between the age of the diamond and the age of the pipe that delivered it can be 2 billion years or more. The volcano that erupted at Kimberley, roughly 90 to 100 million years ago, carried diamonds that had been sitting in the dark beneath southern Africa for 2.5 to 3 billion years before it arrived. They are xenocrysts. That word, xenocryst, means foreign crystal, a crystal that does not belong to the magma that carries it, a passenger rather than a child of the eruption. The diamonds did not crystallize from the kimberlite magma, they were picked up by it, and the keel is what held them for the intervening billions of years, cold enough to keep the graphite to diamond transformation stable, rigid enough not to be convectively scrambled, ancient enough to have been the right depth and the right temperature when the carbon first organized itself into those tight tetrahedral lattices. But the story of how the keel holds diamonds stable requires first understanding why that stability is conditional, why the diamond window, as it is sometimes called, is a window and not an open field. And that understanding requires returning, one more time, to the phase diagram of carbon. Carbon exists in multiple forms depending on the pressure and temperature to which it is subjected. At the pressures and temperatures that prevail near the Earth's surface, carbon's stable form is graphite, the soft, dark, layered mineral that makes pencils write and that flakes apart easily because its atomic layers are held together only by weak forces. But increase the pressure enough while keeping the temperature low enough, and carbon rearranges itself into diamond, in which each carbon atom bonds covalently to 4 others in a 3-dimensional framework so rigid and so strong that diamond is the hardest naturally occurring material known. The boundary between the graphite stability field and the diamond stability field on the pressure-temperature diagram is a line, and that line has a particular trajectory through the combinations of depth and temperature that characterize different parts of the Earth's interior. The mantle beneath young continents, or beneath ocean basins, follows what is called an adiabatic temperature gradient. Essentially, the temperature increases with depth at roughly the rate expected for rock that is slowly convecting, turning over, carrying heat upward. Under those conditions, by the time you reach the depths at which diamond would be stable given the pressure, the temperature is already high enough to push you past the diamond stability field and into the regime where, if carbon is present, it remains graphite. Diamond can form at those depths in the oceanic or young continental mantle, perhaps, under some circumstances, but it cannot persist. The temperature is too high. Under a cratonic keel, the situation is different, and the difference is precisely the cold. The cratonic geotherm, the actual temperature versus depth profile of the mantle beneath an old Archean shield, is anomalously low. Because the keel is so thick and conducts heat so slowly, and because the surface heat flow over Archean cratons is only roughly 40 to 50 milliwatts per square meter, well below the 70 or more milliwatts per square meter typical of younger regions, the interior of the keel stays cold all the way down to depths of 200 kilometres and beyond. And that cold geotherm, when plotted on the carbon phase diagram, passes through the diamond stability field at the relevant depths, below roughly 150 kilometres, above a pressure of roughly 4.5 gigapascals, a gigapascal being roughly 10,000 times atmospheric pressure, and 4.5 gigapascals being the kind of pressure that compresses rock in ways that have no everyday analogue, except perhaps to say that it is as if the entire weight of a column of rock extending from the floor of the deepest ocean all the way back to the surface were pressing on every square centimetre the temperature inside the Kaapvaal keel and the temperature inside the slave keel and the temperature inside the keels of all the world's ancient Archean shields is low enough that diamond is the stable form of carbon. Not graphite. Diamond. That is the diamond window. It is not a metaphor. It is a physical region defined by the intersection of a phase boundary with a particular geotherm, and it exists in the deep earth only where the geotherm is cold, and the geotherm is only cold where the keel is old and thick and depleted. The window is a consequence of the keel, and the keel is a consequence of the Archean Earth's peculiar way of building continents, which left behind a residue so depleted and so dry and so cold that it has hung beneath its overlying crust for 3 billion years as a nearly neutral, nearly invisible, enduring platform on which the surface history of southern Africa has slowly unfolded. T.N. Clifford noticed the pattern before anyone had a complete theory to explain it. In 1966, a geologist named T.N. Clifford published an observation that, in retrospect, contains embedded within it the entire argument about keels and diamond windows, even though the term cratonic keel was not yet in the vocabulary and the seismic imaging that would eventually map those keels had not yet been developed. What Clifford observed, by examining the global distribution of kimberlite pipes and the diamonds they contained, was that economically significant diamond deposits, the pipes that yield enough diamonds in sufficient concentration to be worth mining, occur almost exclusively in kimberlites that have erupted through Archean cratons. Through continental crust older than roughly 2.5 billion years. Kimberlites that erupt through younger crust are mostly barren, or nearly so. Kimberlites through Archean crust are where the diamonds are. This empirical relationship, the direct association between old keels and diamond deposits, became known as Clifford's rule, and it has been confirmed by subsequent study of diamond occurrences around the world. What Clifford's rule means physically, understood in the light of the keel concept, is this: kimberlites that erupt through young or thin lithosphere do not pass through a deep, cold keel. The diamond window in the wall of the pipe they are tearing through is absent or shallow or exists only at depths the kimberlite passes through too quickly to acquire many passengers. But kimberlites that erupt through the thick, cold root of an Archean craton, kimberlites like the ones at Kimberley and Cullinan, travel upward through a column of rock that has been sitting inside the diamond stability window for billions of years. A column of rock that, in those billions of years, has accumulated diamonds wherever carbon was present in the right form, slowly, crystal by crystal, in the darkness and the pressure and the cold. And when the kimberlite arrives, it sweeps those crystals up. The rule is not absolute. Not every kimberlite through an Archean craton is a productive diamond mine. The geometry matters, the precise path the kimberlite follows through the keel, the local concentrations of carbon-bearing material, the history of fluid movement through the rock. Diamond mining is an exercise in geology, economics, and considerable uncertainty. But the absence of significant diamond deposits in kimberlites outside Archean cratons is, as a pattern, remarkably consistent, and it points directly to the keel. There are no diamonds without the window. There is no window without the cold. There is no cold without the depth. And there is no persistent depth without the buoyancy and the strength, the isopycnic balance and the dry high-viscosity olivine that have been the subject of this long descent. Now the second place. Now the north. The Canadian Shield is not a single craton, but an assembly of several, stitched together by the processes of the Archean and early Proterozoic into the broad, lake-scattered, largely flat surface that covers much of central and northern Canada. It is among the most extensive exposures of Archean crust on the planet, and within it, toward its northwestern edge, lies a piece of geology that has drawn the attention of researchers interested in the very oldest chapters of Earth history. The Slave Craton, in what is now the Northwest Territories of Canada, is a relatively small Archean block, but it holds a particular distinction. The rocks of the Acasta Gneiss, outcropping in a remote area west of Coronation Gulf, have been dated by uranium lead methods applied to zircon crystals within them to approximately 4.03 billion years, making them among the oldest intact pieces of continental crust so far identified on the surface of the Earth. 4.03 billion years. The planet itself is approximately 4.54 billion years old, and the Moon, which formed in the aftermath of a collision between the proto-Earth and a Mars-sized body early in solar system history, is roughly 4.5 billion years old. The Acasta Gneiss, then, is rock that crystallized and survived from a time when the planet was barely 100 million years past that catastrophic collision, when the surface was still geologically violent in ways that have left almost no direct record, when the Archean crust that would eventually become the continental nuclei of today was just beginning to accumulate. And some of that earliest accumulation, in the form of the Acasta Gneiss, is still there, still at the surface, still a piece of the Slave Craton, still underlain by the cold, depleted keel that has kept it from being destroyed. The keel beneath the Slave Craton has been imaged seismically, and it extends, like the keels beneath other Archean shields, to depths in the range of 200 kilometres or more. It is cold. It returns fast shear wave velocities to the seismometers listening at the surface. And it is the reason, as much as any other factor, that the Acasta Gneiss is still here to be measured. Beneath the Slave Craton, within the diamond stability window maintained by that cold keel, lie two of the largest diamond mines in the Western Hemisphere. The Diavik mine, which began production in 2003, and the Ekati mine, which began production in 1998. Both sit on Lac de Gras in the Lac de Gras district of the Northwest Territories, and both are kimberlite pipe operations, extracting diamonds from pipes that rose through the Slave Craton's ancient lithosphere. The pipes are relatively young. The kimberlites at Ekati and Diavik erupted somewhere in the range of 40 to 80 million years ago during the Cretaceous period, when dinosaurs were still present on the surface of the same continent. But the diamonds they carried up were, by the time of that eruption, already ancient things, formed in the cold darkness of the slave keel at some point that Rayos and Esmond measurements on their inclusions place in the range of hundreds of millions to billions of years before the eruption arrived. The pattern is the same as in southern Africa. The keel holds the diamond, the kimberlite delivers it. The craton's age determines whether the pipe passes through the window. And then there is the Superior Craton, which is by some measures the largest single Archean block on Earth, stretching across much of what is now Ontario and Quebec, and extending beneath the Great Lakes and into parts of the northern United States. It is not, primarily, a diamond province in the way the Slave Craton is. The geometry of kimberlite intrusion and the precise configuration of the keel mean that productive diamond mines are not evenly distributed across all Archean terrains. But the Superior Craton is relevant here, not for its diamonds, but for what it tells you about the scale of the thing. These are not small patches. The Archean cores of the continents are vast. The Superior Craton alone covers roughly 1.5 million square kilometres of Canada. The Canadian Shield as a whole, including the Slave, Superior, and other Archean and Proterozoic elements, covers a substantial fraction of the second largest country on Earth. And all of it, all of that surface, all of those lakes and forests and exposed rock faces and mining operations and research stations, sits above a keel, a cold, depleted, ancient route reaching down 200 kilometres or more into the mantle, hanging in its nearly neutral buoyancy, held there by the balance between the thermal density it accumulated by being cold and the compositional buoyancy it acquired when the Archean earth melted the iron-rich fraction out of it 3 billion years ago. The Kaapvaal and the Slave and the Superior are names that appear in the scientific literature with a frequency that reflects how thoroughly they have been studied, how many drill cores have been pulled from their interiors, how many isotope ratios have been measured from their xenoliths, how many seismic experiments have traced the shape of their keels. But they are not the only ones. Clifford's observation about diamonds and old cratons applies globally because old cratons are global. There are roughly 35 major Archean cratonic blocks identified on the planet's surface or inferred from geophysical data beneath younger overlying cover. The Siberian Craton, which underlies much of central Russia and whose kimberlites, particularly those of the Yakutia region, have made Russia one of the world's major diamond producers. The Fennoscandian Craton, the old Archean core of Scandinavia and Finland and the Russian northwest, whose shields outcrop in the ancient rounded hills of the Baltic landscape. The Amazonian Craton, whose old heart underlies much of the Amazon basin, mostly buried beneath the river's sediment and the rainforest above it. The West African and Congo Cratons of equatorial and western Africa. The Dawa Craton of southern India, one of the oldest pieces of the Indian subcontinent, which rode the long journey north from Gondwanaland before colliding with Asia. The Pilbara and Yilgarn Cratons of Australia. All of these are old, all of them are underlain by keels. All of them have, to the extent that they have been studied, returned ages for their mantle roots that broadly match the ages of the crust above, confirming, craton by craton, the pattern established most firmly at the Kaapvaal, that the keel and the crust are one raft, born together, preserved together, and that the preservation of the crust across billions of years of Earth history is in large measure a function of the persistence of the keel beneath it. And yet it is worth pausing here, in this part of the descent, on a particular detail of the diamond story, on the mechanics of the moment when the keel's long patience ends and the kimberlite arrives. The ascent of a kimberlite from the base of the lithosphere to the surface is not a gentle process. Kimberlite magmas are carbon dioxide rich and volatile laden, and as they rise through the overlying rock they decompress, and the volatiles exsolve from the melt, and what began as a pulse of magma rising through fractures in the deep crust becomes, in the upper levels, something more like an explosive column of gas-charged rock that tears a widening path upward and erupts at the surface in a manner that has been compared, at least structurally, to certain kinds of volcanic explosion. Though kimberlite eruptions are not necessarily catastrophic in the way that the word explosion might suggest. The resulting structure is a pipe, a diatreme, that shape that has been described as carrot-shaped, wide at the top where the eruption scattered its material across the surface, narrowing downward into the throat through which the magma rose. The walls of that pipe are the rock through which the kimberlite tore, and embedded in the kimberlite that fills it are the fragments it tore loose along the way, the xenoliths and the diamonds. The speed of ascent matters enormously to the diamonds, and it is worth understanding why. Diamond is the high-pressure, low-temperature form of carbon. Graphite is the low-pressure form. The boundary between them on the phase diagram means that as a diamond rises from the depths carried by a kimberlite magma, it passes through conditions, shallower depths, lower pressures, at which diamond is no longer thermodynamically stable, at which the dense, cubic lattice of diamond wants to relax into the layered, softer structure of graphite. If the diamond rises slowly enough, at temperatures high enough, that transformation can proceed. The carbon in the diamond will reorganize, and what arrives at the surface will not be diamond but a pseudomorph, a shapeless remnant, a ghost of the geometry that once existed. Slow, hot ascent destroys diamonds. Fast ascent preserves them. The kimberlite ascends fast, meters per second. From depths of 150 to 200 kilometres or more, rising at that rate, the journey to the surface takes on the order of hours, perhaps less than a day. And because the ascent is so rapid, the diamond crystal does not have time to convert. The pressure drops, but the conversion kinetics are too slow at the temperatures prevailing in a fast-moving kimberlite for the transformation to graphite to proceed. The diamond arrives at the surface still a diamond, still sealed, still carrying inside its lattice the inclusions that record the conditions of the deep earth at the time it formed. Conditions that might be 3 billion years in the past. The contrast between the age of the diamond and the age of the pipe that delivered it is, when you hold both numbers in mind simultaneously, one of the more vertiginous pieces of arithmetic that the geology of the keel produces. At Icati, a kimberlite erupts somewhere around 50 to 60 million years ago. It carries diamonds whose inclusions return ages of 1 to 2 billion years. The diamond waited, in the cold and the dark, inside the slave keel for something between 900 million and 2 billion years between the moment of its formation and the moment the magma arrived. It waited through the entire Phanerozoic, through the Cambrian explosion of complex animal life, through the age of fish, and then the age of forests, and then the age of dinosaurs, and then the age of mammals, without those eons touching it. The geological events that reshaped the surface of the planet above it came and went. The Slave Craton drifted slowly across the face of the Earth as the continent of which it is a part moved through the planetary interior's slow convective rearrangement. And the diamond stayed where it was, locked in the cold stability of the keel, waiting. That is not a metaphor for patience, it is a physical record of it. The diamond's persistence is the persistence of the conditions that preserved it, which is the persistence of the keel, which is the persistence of the balance, the cold fighting to sink the root, the depletion fighting to float it, the two nearly cancelling, the root hanging. There is one more detail of the diamond story that belongs in this movement, before the narration turns to the larger contrast that the title promises, the contrast between the enduring continent and the endlessly recycled seafloor. It is a detail about what the diamonds contain, and it points toward territory that this part of the descent will approach but not fully enter, because what lies in that direction is the subject of the movement that follows. The inclusions in diamonds are not all the same. They fall into two broad families whose differences tell different stories about the history of the keel and about the broader history of the planet. Peridotitic diamonds, called P-type, grow in the harzburgite and dunite of the depleted keel itself, the iron pore. Magnesium-rich residue that Thomas Jordan recognized as the compositionally distinct root. Their inclusions are minerals characteristic of that depleted peridotite, olivine, enstatite, chromium pyrope garnet, chromite, and their ages, as measured by Oz on sulfide inclusions, are typically very old, Archean and Proterozoic, spanning the range of 1 billion to more than 3 billion years. Closely matching the ages of the keel material itself, they are, in the most literal sense, diamonds of the keel. Born in it, preserved by it, delivered from it. But there is a second family. Eclogitic diamonds, E-type, have inclusions not of depleted peridotite, but of minerals characteristic of eclogite, garnet and clinopyroxene, with chemical signatures that resemble, when interpreted carefully, the metamorphosed products of ancient oceanic crust that was once at the surface of the ocean floor and was then subducted, dragged down into the mantle by the same process that destroys modern oceanic crust at the boundaries of tectonic plates, and lodged, eventually, in or near the base of the cratonic lithosphere. The carbon in those eclogitic diamonds often carries isotopic signatures in its carbon-13 to carbon-12 ratio that suggest it was once organic material, biological carbon, that lived near the surface of the ancient ocean and was carried to depth when the seafloor of which it was a part descended into the mantle. The significance of the eclogitic diamonds, in the context of this narration, is what they suggest about when the process of plate tectonics, of crustal subduction, of one piece of lithosphere descending beneath another, was operating on the early Earth. Because some of those eclogitic diamonds return ages that are Archean, ages of 2.5 to 3 billion years or more, their existence at that depth at that time implies that the surface material of which they carry a signature was being subducted into the mantle that long ago. The diamonds are, in this reading, a record of the early onset of the very process that recycles oceanic crust, and that the keel is largely immune to. The two stories, the story of the keel's endurance and the story of the ocean floor's endless recycling, are, at their root, the story of two different fates for two different kinds of lithosphere and the eclogitic diamonds. Locked in the Archean keel are evidence that the divergence of those fates was already underway when the keel itself was young. But that is, again, the edge of the territory that the next movement opens into more fully. For now, in this part of the descent, the point is simpler and more concrete. There are two kinds of diamond, and both of them, P-type and E-type, come from the keel. Both of them are ancient. Both of them were waiting in the cold, deep root for hundreds of millions or billions of years before the kimberlite arrived. Both of them are, by Clifford's rule, found in abundance only where the keel beneath the craton is old enough and cold enough to maintain the window in which they can survive. And the fact that you can hold one in your hand, that a stone formed 3 billion years ago in the darkness of a root 200 kilometres below the surface of southern Africa, can be extracted from a mine in the Kaapvaal and cut and polished and placed against a light, is a consequence of an improbable chain of physical circumstances beginning with the near-perfect cancellation of two competing tendencies in a depleted, cold, ancient body of mantle rock. The keel floated. The kimberlite rose fast. The diamond survived. And somewhere beneath your feet, if you live anywhere on a continent, beneath the soil and the bedrock and the shallow crust and the deeper crust and the 100 kilometres of lithosphere above the depleted root, there is a body of cold, ancient, nearly neutrally buoyant rock that has been holding the surface above the fire since before the first recognizable ancestor of any complex living thing had yet to exist. You cannot feel it. You cannot hear it. You cannot, in ordinary life, know it is there. But the keels are there. All 35 of the major Archean blocks and the smaller fragments and Proterozoic additions stitched between them, all of them sitting in their particular balance, conducting heat slowly upward through their thick, cold interiors, resisting the convecting mantle below, keeping the surface they carry from being pulled down and recycled into the heat. And the contrast with what lies beneath the ocean, what does not endure, what cannot endure, what is continuously born and continuously destroyed in the endless slow churning of the plate system, that contrast is where this narration is moving next, into the part of the argument that gives the title its fullest meaning. Consider the floor of the Pacific Ocean. It is, by almost any measure, an impressive thing. It is vast, far larger in area than all the continents combined, and it is in constant motion, spreading apart at mid-ocean ridges where new basaltic rock wells up from below, cooling and thickening and sliding slowly away from the ridge crest like a conveyor belt running imperceptibly toward the far edges of the basin. New seafloor is being made right now as you listen in the dark. And at the edges of the basins, where the old, cold, dense oceanic plate finally reaches a continental margin or an island arc, it bends downward and slides back into the mantle from which it came, carrying with it whatever sediment and seawater and biological material happened to be resting on its surface at the moment it descended. The ocean floor is created, it travels, it is destroyed, it is returned to the interior of the planet. And then the process begins again. Nothing on the ocean floor is older than roughly 180 million years. That is the number worth sitting with for a moment, because it is almost impossible to make it feel as strange as it actually is. 180 million years ago, the dinosaurs were approaching their long zenith. The continents were still partly assembled into Pangaea, beginning the slow splitting and drifting that would eventually arrange them into something approaching the shapes we now carry in our heads from maps. The Atlantic Ocean was, in geological terms, barely a seam. And the oldest surviving piece of oceanic crust, sitting now in the deep western Pacific or in a corner of the eastern Mediterranean, was not yet born. Everything older than that, every square kilometre of seafloor that existed before that moment, has been subducted. It has been dragged back into the mantle and melted and stirred back into the planetary interior, and no direct record of it remains anywhere on the ocean floor. The continents reach back 4 billion years. That is the contrast the title is pointing toward. That is the asymmetry that the keel explains, and the reason for it is, at its root, a matter of density, of what floats and what sinks in the particular gravitational arithmetic of a planet whose interior is layered by weight. Oceanic crust is made of basalt. Basalt is dark and fine-grained and rich in iron and magnesium, and its density is roughly 3 grams per cubic centimetre, close enough to the mantle beneath it that, when it cools and thickens at the base of aging oceanic lithosphere, the whole package can eventually become denser than the astenosphere below and begin to founder. It does not take much. The mantle sits at roughly 3.3 grams per cubic centimetre in the upper regions where subduction begins, and oceanic lithosphere, cold and old and thick, can exceed that. When it does, gravity does the rest. The plate bends and descends, pulled by its own weight in a process geologists call the slab pull, and it slides into the interior, and it is gone. Continental crust is made of granite and its relatives, silica-rich, aluminum-bearing, pale, low-density rock sitting at roughly 2.7 grams per cubic centimetre, which is noticeably lighter than either oceanic crust or mantle. It is, in a meaningful sense, the slag that floated to the top when the interior differentiated, the low-density fraction that rose and stayed, accumulating over billions of years of volcanism and accretion into the thick, pale, light-coloured masses of the shield regions. And beneath that already buoyant crust, as this narration has been tracing for some time now, there is the keel, the depleted, dehydrated, chemically lightened mantle root that extends another 150 to 250 kilometres downward, further lightened relative to the surrounding mantle by the removal of its iron-rich basaltic fraction. Think of an iceberg. The part you see above the waterline, the brilliant white mass catching the light, is only a fraction of the whole. Below the surface, invisible, the body of the ice extends downward into the water for roughly 7 times the height of what you see above. The iceberg floats because ice is less dense than seawater, and so the whole assembly, the visible peak, and the vast hidden body below, sits in its particular balance, buoyant, rising and falling with the slow swell, but never sinking. The continent is the same, in its way. The crust is the visible peak, the part of the iceberg you can stand on. The keel is the enormous body below, hidden, extending deep into the denser mantle around it, and the whole assembly, crust above, depleted root below, is too light, collectively, to be dragged under and held down. When subduction pulls on a continental margin, it can shave off sediment, it can buckle and thicken the crust into mountain ranges, it can do a great many dramatic things. But it cannot, in general, pull the full continental package below and keep it there. The continent is too light, it bobs back up. And so the deep geological record, which is nowhere on the ocean floor, is everywhere on the continents, in the ancient gneisses and the greenstone belts, and the banded iron formations, and the oldest known exposures of continental crust. Lying on the surface in places like the Canadian Shield, patient and incomprehensibly old. That is what the title means by riding above the fire. Not that the continents have simply avoided the fire, they are surrounded by it, underlain by it, in constant contact with the slowly convecting astenosphere that is the planetary engine driving the whole plate system. But they ride above it, sustained by buoyancy, anchored by the cold and depleted keels that keep their roots neutrally poised in the denser mantle around them. Resistant to the flow, resistant to the heat, resistant to the forces that have erased and recycled every square kilometre of ocean floor that has ever existed. And yet, the keel can die. That sentence deserves its own silence, because the whole structure of this argument, the long, careful assembly of reasons why keels endure, the near-perfect cancellation of cold and depletion, the dryness and strength of cratonic olivine, the billions of years of stability, all of it would be incomplete without the acknowledgement that the mechanism can fail. And the most dramatic, best-studied case of that failure is not some remote theoretical scenario, it is the eastern portion of what is called the North China Craton, which was once a full, thick, ancient Archean cored block of continental lithosphere with a keel extending perhaps 200 kilometres into the mantle beneath it, and which, during the Mesozoic and Cenozoic, the last 200 million years or so of Earth history, lost most of that keel. The geological term for what happened to the North China Craton is decratonization, lithospheric thinning. The keel, which had been there since the Archean, which had survived multiple supercontinent cycles, and the long, slow churning of the mantle through hundreds of millions of years of geological history, was removed. It thinned from roughly 200 kilometres to somewhere under 80 kilometres, in places perhaps much less, and the result was everything you would expect if the argument about keels and stability is correct: increased volcanism, rifting, the formation of extensional basins, enhanced heat flow at the surface, and the wholesale destruction of the ancient stable craton architecture that had once characterized the region. Where the keel was, there is now a lithosphere far thinner and weaker and warmer than any true craton should possess. How does this happen? How does something that has endured for 3 billion years cease to endure? The answer involves a process called metasomatic refertilization, and it is, in a sense, the precise reverse of the depletion that created the keel in the first place. Recall that the keel is buoyant because the melt fraction, the iron-rich basaltic material, was extracted from it in the Archean, leaving a residue that is lighter and drier and stronger than fertile mantle. Metasomatism is the infiltration of that residue by new melts and fluids, rising from below or introduced laterally by tectonic events that add back iron and other components, increasing the density of the root and, crucially, reintroducing water. And water, as everything said earlier in this narration about olivine rheology implies, is exactly what you do not want in a keel if you want it to remain strong and buoyant and resistant. When iron is added back, the density rises. When water is added back, the viscosity drops. The keel becomes denser than it was, heavier, less able to maintain its isopycnic balance against the thermal density increase from being cold. And it becomes weaker, more easily deformed, more susceptible to being entrained by the convecting mantle below, or to simply detaching and sinking. A process called delamination, leaving the crust above suddenly, without its ballast, without its insulation, without its deep foundation. The surface above a delaminating keel can collapse, or it can dome upward as the hot astenosphere rushes in to fill the space left by the departing root. Volcanism erupts through pathways newly opened by the thinning lithosphere. Heat flow rises, the thermal blanket provided by the thick cold keel is withdrawn, and the whole region is fundamentally altered. In the case of the North China Craton, the trigger for refertilization and thinning appears to have involved the subduction of the Pacific Plate and related tectonic events that introduced melts and fluids into the base of the ancient root. The details are still debated, as the details of most things at these depths and timescales are debated. But the broad outline is not in serious dispute. The keel was there, it was thick, it was ancient, and then it was not. And the contrast between the stable western part of the North China Craton, which still retains something of its original lithospheric thickness, and the thinned and altered eastern portion makes the comparison vivid and instructive within a single geological block. The North China Craton is, in this sense, the exception that clarifies the rule. Everything argued about keels, that they are buoyant because they are depleted, that they are strong because they are cold and dry, that their survival across billions of years is a consequence of these specific physical properties held in near-perfect balance, all of that is confirmed, not contradicted, by the North China case. Because what the North China case shows is that when those specific properties are compromised, when the depletion is reversed and the dryness is relieved and the balance is tipped, the keel does exactly what it should have done all along if those properties had never been in place. It sinks, it is removed, the continent above it loses its ancient character. The stability that seemed permanent was, all along, conditional, dependent on the maintenance of the balance that the Archean created. And that Archean creation, the original making of the keels, is itself something that deserves attention. Because it is not simply a neutral geological fact, it is a consequence of something specific about the early Earth, a condition that has not been replicated since in quite the same way, and whose unrepeatable character is part of why cratons exist at all. The Archean mantle was hotter than the mantle today. Not dramatically hotter, this is a matter of tens to perhaps 100 or more degrees Celsius at most depths, but hotter in a way that made a specific and important difference to how rocks melted within it. When hot mantle rises toward the surface, whether at a mid-ocean ridge or above a mantle plume, it melts because decompression lowers the pressure and allows solid rock to pass into liquid. The degree of melting, what fraction of the rock actually liquefies, depends on how hot the mantle is and how far it rises before solidifying again. A hotter mantle melts more completely. It produces a larger fraction of melt. And crucially, it extracts more of the basaltic fraction from the residual solid that remains behind. In the Archean, this process operated at higher temperatures, and so the melt fractions extracted from the rising mantle were larger, and the residues left behind were more thoroughly depleted of iron, aluminum, and calcium than anything the present mantle typically produces. The Archean was, in effect, a more efficient factory for making the particular kind of rock, the harzburgite, the iron poor, magnesium-rich, dry depleted peridotite, from which lasting keels are constructed. The magnesium numbers of Archean cratonic mantle xenoliths, those deep rock samples carried up by kimberlites, are typically in the range of 92 to 94, far higher than the 89 or 90 typical of modern fertile mantle, and that difference, which represents a greater removal of iron, corresponds to a greater degree of melt extraction that the hotter Archean mantle was uniquely positioned to accomplish. This is why cratons are overwhelmingly Archean. Not exclusively. There are Proterozoic additions and some younger mobile belts that have been welded onto cratonic margins, but the thick, stable, diamond-bearing cores that have survived intact for the longest, that carry the deepest and most ancient keels, are without exception Archean in age, built during a window of Earth history when the planetary interior was hot enough to produce the right residue in sufficient quantity to create a keel that could endure. The recipe required conditions that have since cooled away. And so the cratons we have are, in a sense, relics not only of ancient time, but of an ancient planetary state, objects produced by a hotter, differently organized early Earth, preserved precisely because their unusual physical properties allowed them to survive the cooling and reorganization of the billions of years that followed. The world, in other words, could not easily make a new Kaapvaal. It could not easily make a new Canadian shield. The mantle is no longer hot enough to extract sufficient melt to produce the right depleted, dry, light residue at the necessary scale and depth. What exists is what was made, and what was made is old. 3.5, even approaching 4 billion years old in the deepest and most ancient parts of the remaining keels. And it has been sitting in its balance ever since, slowly cooling, slowly conducting the heat of the deep earth up through its thick, cold interior toward the surface, resisting the convection below, keeping the continents afloat. And in the deepest, coldest interior of those keels, in the long corridors of olivine and harzburgite extending 200 kilometres below the surface, and in some cases far beyond, the diamonds wait. Or rather, the diamonds have waited. For some of them, the waiting has lasted 3.5 billion years. There are diamonds that were not born in any keel. There are diamonds whose origins lie so far below the base of any lithosphere, so deep in the interior of the planet, that they bear almost no relationship to the story of cratons and stability and buoyancy described here. These are called superdeep diamonds, and they come from the mantle transition zone and from the lower mantle itself. From depths of 300 to 800 kilometres below the surface, regions where the pressure is so extreme that the mineral chemistry of rock is utterly different from anything that exists in the crust or in the lithosphere above. In 2014, a team of researchers led by Graham Pearson published a study in the journal Nature describing a diamond that contained, sealed within it as a microscopic inclusion, a mineral called ringwoodite. Ringwoodite is not an exotic name to a mineral physicist. It is a high-pressure form of olivine that exists in the transition zone, the region of the mantle between roughly 460 kilometres deep. But until that study, no sample of ringwoodite had ever been recovered from a natural geological context on the surface of the Earth, because ringwoodite only exists at pressures corresponding to those depths and transforms into other minerals when brought toward the surface. This particular grain, sealed inside a diamond, had survived the journey. And it was not the mineral alone that made the study remarkable. It was the water. The ringwoodite inclusion contained water, hydroxyl groups incorporated into its crystal structure, in a concentration suggesting that the surrounding mantle transition zone might carry, globally, a quantity of water comparable to several times the volume of all the surface oceans. Not liquid water, not a hidden underground sea in any simple sense, but water chemically bound into the crystal lattice of the minerals that constitute the deep mantle, stored there under conditions of extreme pressure and temperature, cycling slowly between the deep interior and the surface through the long geological processes of subduction and volcanism. And in 2018, another study reported the discovery of ice, a form of ice called Ice 70, stable only at pressures far beyond anything found near the Earth's surface, as inclusions inside diamonds. Ice V7 requires pressures equivalent to those found at depths of several hundred kilometres, and its presence inside diamonds confirmed that water does indeed exist, in one form or another, at those extraordinary depths, carried there by subducted oceanic plates that drag surface seawater down into the interior. This is the deep water cycle, and it is one of the most unexpected and profound things that diamonds have revealed about the planet. The water in the ocean is not simply sitting on the surface, cycling between atmosphere and sea, and river and glacier. Some fraction of it, over the billions of years of geological time, has been carried downward by subducting plates, sealed into the crystal structures of high-pressure minerals, transported into the deep interior, and eventually returned through volcanism and other processes to the surface. The planet breathes water over geological time, cycling it between the surface and the deep interior and back again, and the diamonds are the evidence. Ordinary diamonds, the ones from the keel, the ones from the diamond stability window that lies between roughly 150 and 200 kilometres depth, tell a different story, though one no less remarkable. These diamonds are time capsules in the most literal sense available in geology, because diamond is the hardest natural mineral, because its crystal lattice is essentially impermeable to diffusion at any temperature found within the lithosphere, and because it can physically seal within it whatever solid inclusion it traps at the moment of crystallization, a diamond formed 3 billion years ago carries, perfectly preserved within its rigid interior, a sample of whatever mineral or fluid happened to be in contact with it at that moment in deep time. The sulfide inclusions in peridotitic diamonds, the P-type diamonds formed in the depleted harzburgite of the ancient Keel, have been dated by the rhenium-osmium system and yield ages reaching 3 billion years and beyond, ages that match the age of the Archean crust above them and the xenolith peridotites that surround them. These diamonds grew in the Keel when the Keel itself was young. They grew in a body of cold, depleted, buoyant rock that was already establishing its long equilibrium with the surrounding mantle, and they have been there ever since. Sealed in the pressure and temperature conditions of the diamond stability field, preserved by the very coldness and thickness of the root that makes diamonds possible at all. The eclogitic diamonds, the E-type diamonds, formed not in depleted harzburgite, but in eclogite, a high-pressure metamorphic rock made of garnet and clinopyroxene, tell a different and in some ways even stranger story. Eclogite is what basaltic oceanic crust becomes when it is subducted to sufficient depth. The minerals transform under high pressure into the dense, garnet-bearing assemblage we call eclogite. And eclogitic diamonds, which form in that material, carry within them chemical signatures, isotopic compositions of carbon and sulfur, for instance, that point to surface-derived material, sediment, seawater, biological carbon, the chemical fingerprints of the surface world, buried and transformed and locked inside a crystal at depth. When Stephen Shirey and James Richardson studied the ages and chemistry of eclogitic diamonds in the early 21st century, they found something striking. The oldest eclogitic diamonds, with their subducted chemical signatures, appeared in the record at roughly 3 billion years ago, which is, they argued, approximately when something recognizable as modern plate tectonics, with its subduction of oceanic crust to lithospheric depths, became a widespread global process. The diamonds remembered. The chemical signatures preserved in those E-type diamonds, locked in their rigid lattices for 3 billion years, are among the oldest direct evidence we have that subduction was happening. That oceanic crust was being dragged below the surface and lodged in the deep lithosphere at that time and in those places. The diamonds are not merely pretty stones from the deep. They are an archive of early planetary history, a record of events at depths that no drill has ever reached and no direct observation will likely ever achieve. And all of this, the isopycnic balance, the dry, strong olivine, the same age proof of crust and keel, the diamond window and Clifford's rule, the ancient hitchhikers and their billion-year wait, the superdeep ringwoodite and the water it carried from the transition zone, the eclogitic diamonds remembering the onset of subduction, all of it reduces, in the end, to a single improbable fact about this planet. The oldest things on Earth are not on the ocean floor. The ocean floor has no memory older than roughly 180 million years. The old things are here, on the continents, held in place by keels that were built when the planet was young and hot and producing depleted residues at a scale it has never repeated, and have been sitting in their balance ever since, resisting the fire below, insulating the cold and the carbon and the ancient chemistry of their interiors against the heat and the convection and the slow churning of the tectosphere that surrounds them. Consider that, for a moment, in terms of what it means for the existence of a geological record at all. Without the keels, the continents would behave more like the ocean floor. They would be thinner, denser, less buoyant. They would be more susceptible to subduction, more likely to be dragged under and recycled. The surface record of the early Earth, the ancient gneisses of the Canadian Shield, the stromatolites of the Pilbara, the banded iron formations of the Kaapvaal, the Acasta Gneiss of the Slave Craton, 4,030,000,000 years old, would not exist. It would have been carried down and melted and returned to the interior along with everything else. The planet's memory would begin, like the ocean floor's memory, somewhere in the last 200 million years. The geological record would begin, in effect, at roughly the time the first flowering plants appeared. Everything older than that, the entire 4 billion-year history of the crust, the record of the early atmosphere and the early ocean, the oldest fossil evidence of life, the isotopic signatures of processes that shaped the planet's interior in its first billion years, survives because the Keels survived. Because 35 or so major Archean blocks and the smaller fragments between them have been floating in their particular balance long enough to carry the surface record through the supercontinent cycles, through the opening and closing of ocean basins, through the mass extinctions and the ice ages, and the long, slow changes in atmospheric chemistry that constitute the history of a living planet. The Keels are, in a sense, the planet's filing system. They kept the oldest pages, and the diamonds are the footnotes, the precise, unalterable citations buried in the text of the Keel's interior, surviving unchanged for billions of years in the only environment on Earth where the pressure and temperature allow them to exist in stable form, waiting for a kimberlite to rise fast enough to bring them to the surface without reverting to graphite, carrying inside them the chemical memories of the world as it was when they formed. That a human being can hold such a stone in their hand, that the rapid, improbable ascent of a kimberlite diatreme can deliver from a depth of 150 kilometres, in a matter of hours, a crystal that has been sealed in cold rock since the Archean, is one of the odder consequences of the physics described in this narration. The keel kept the diamond stable. The keel kept the kimberlite cold enough and the diamond window cold enough to preserve the carbon in its high-pressure form rather than allowing it to transform back to graphite. And then, at some moment in the relatively recent geological past, 100 million years ago, 200 million years ago, the kimberlite volcanism of a given region tends to cluster in particular periods, but no single date is universal. The kimberlite rose through the keel, ripping loose fragments as it went, carrying the diamond upward through the pressure gradient faster than the crystal could transform, and depositing it in a carrot-shaped pipe of shattered rock at the surface, where, after the erosion of geological ages, it was found. The keel held it, the eruption freed it, the speed preserved it, and somewhere in the deep interior of the Kaapvaal Craton, or the Slave Craton, or the Siberian Craton, or the Fennoscandian Shield, or the ancient lithosphere beneath the Indian subcontinent, where the Dawa Craton has sat for over 2.5 billion years. In the cold, slow, thick rock of the keel, there are diamonds still forming, or waiting, sealed in the same pressure and temperature conditions in which they have always sat, in a body of rock whose temperature has changed almost imperceptibly over the billions of years of its existence, held in the balance between cold and depleted, between heavy and light, between the pull of gravity and the ancient chemistry of a hotter Earth's discarded residue. They are there now, as you listen to this, in the dark. The mantle convects slowly below the keels, carrying heat from the deep interior outward in the slow, patient, inexorable circulation of rock that moves at the speed of fingernails growing and operates on timescales that make the word slow seem almost comically inadequate. The keels sit above that circulation, cold and rigid and barely denser than the mantle around them. Barely, but enough. extending their thick roots down through the lithosphere and into the uppermost regions of the convecting mantle, feeling the heat from below and conducting it upward through the thick, slow column of depleted rock, releasing it at the surface at the rate of 40 to 50 milliwatts per square metre, low, almost indetectable, the cool exhalation of a very old, very stable, very cold interior. Above the keels, the continents carry their accumulated history, the mountains and the river valleys and the sedimentary basins and the ancient eroded crests of ranges that were once as high as the Himalayas and are now barely hills, worn down over hundreds of millions of years to the gently rolling shield landscapes of the Canadian North, or the flat Precambrian plains of interior Africa, or the red and ancient outcrops of the Pilbara in Western Australia, where stromatolites built by communities of microbes 3.5 billion years ago are still visible in the rock, in the surface expression of one of the oldest stable platforms on Earth, sitting on its keel, going nowhere. The planet is very old. The keels are older than almost everything on its surface, and the quiet, slow, physically improbable fact of their survival, the fact that cold rock, which should sink, does not sink because a second property almost exactly cancels the first, and the resulting neutral buoyancy has been maintained for 3 billion years through supercontinent cycles and glaciations and the evolution of every form of complex life that has ever existed. That fact is one of the more remarkable and least celebrated things about the world you are lying in right now. You are on a continent. The continent is old. Beneath it, far beneath it, in the cold and silent interior of a keel that has been there longer than any animal or plant or ocean that now exists, there is rock that has not changed appreciably since before the Cambrian, before the first fish, before the first multicellular organism complex enough to leave a recognizable fossil, before almost everything that most people mean when they say the word life. And in that rock, in the carbon held under pressure, in the diamond stability window, there are crystals that remember. The fire is still there, below the asthenosphere still convects, still carries heat outward from the deep interior, still shapes the surface through the slow machinery of the plates. But the keels sit above it, as they have always sat, in their particular balance, cold enough to be strong, depleted enough to be light, dry enough to resist the churning, and the continents ride above the fire, and the diamonds wait in the dark, and the long, unhurried, incomprehensibly ancient story of the deepest part of the solid earth continues undisturbed in the rock beneath everything. If you feel moved to share where in the world you are listening from tonight, the comments are there, and they are read with genuine interest and care. This is a strange and enormous planet, and knowing where someone is lying in the dark, beneath some fragment of its ancient surface, above some portion of the old geology described in this narration, is a small and pleasant thing to learn. There are more stories here of this same slow and careful kind, waiting for whenever you want them. The keels are beneath you, old, cold, and holding. History will still be here in the morning. For now, rest.